Hi, thanks for joining me. Today I've got a fun number theory problem I want to solve. This is the 2018 AIME 1 and this is problem 11. We want to find the smallest natural number n, so smallest positive integer n, such that when we write 3 to the n in base 143, its last two digits are 0, 1. Okay, so we're going to write 3 to the n base 143, and then we want the smallest such n such that when we write that number out, the last two digits, so the digits 2 to the right, the two last digits most rightwards, if that makes any sense, are 0 followed by 1. Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so the first thing I guess we notice is that this problem here is equivalent to saying we want to find the smallest n such that 3 to the n is congruent to 1 mod 143 squared. Okay, but 143, that's just 11 times 13, sorry, so 143 is just 11 squared times 13 squared. Now, 11 and 13 are both prime numbers, and in particular they're co-prime from one another, so that means that 11 squared and 13 squared are co-prime. So this guy here, 3 to the n being congruent to 1 mod 11 squared 13 squared, is the same as 3 to the n being congruent to 1 mod 11 squared, and 3 to the n being congruent to 1 mod 13 squared. Okay, so another sort of equivalent stating is 3 to the n must be congruent to 1 mod 11 squared, and 3 to the n is congruent to 1 mod 13 squared. Okay, so now we're going to find the smallest such n satisfying this last thing here, but remember it's all equivalent. So we're going to find the smallest n such that 3 to the n is congruent to 1 mod 11 squared, and 3 to the n is congruent to 1 mod 13 squared. Okay, so I'm going to deal with each of these separately. Firstly, looking at the 11 squared, and then once I've done that, we'll move on to the 13 squared. Okay, so we want to find the smallest n such that 3 to the n is congruent to 1 mod 11 squared, but 11 squared, of course, is just 121, and we need that 3 to the n is congruent to 1 mod 13 squared. So let's look at this guy first, 3 to the n being congruent to 1 mod 121, and to sort of work out what this leads to, we're just going to have a bit of exploration. We know that 3 to the 1 is just 3, which of course is congruent to 3 mod 121, 3 squared is 9, 3 cubed is 27, 3 to the 4 is 81, now 3 to the 5 is 3 times 81, which is 243, but 243 is equal to 2 times 121 plus 1, so of course this guy here is congruent to 1 mod 121. All of these are mod 121. Okay, so we see 3 to the 5 is congruent to 1 mod 121. Okay, and because none of these numbers here are 1 mod 121, what this tells us is that if 3 to the n is congruent to 1 mod 121, then then n must be a multiple of 5. Because if we look at, say, 3 to the 6, we're going to get 3 times, it's going to be the same as 3 times 1, which is 3. 3 to the 7 is going to be 3 times 3, which is 9. And you can see we're going to loop back down this list and keep going around sort of in a loop. So for 3 to the n to be congruent to 1 mod 121, it must be that n is a multiple of 5. Okay, so we've sort of deduced one condition from this equation here, in that n must be a multiple of 5. Okay, so we have n is a multiple of 5, but of course that doesn't mean that n equals 5, because we still have to make sure we satisfy this condition on the right hand side. So we have that n is a multiple of 5, or in other words, 5 divides n. Now we want to look at 3 to the n being congruent to 1 mod 13 squared, and to see this, the first thing I guess we're going to notice is that 3 cubed, that's 27, but that guy is just 13 times 2 plus 1. Okay, so if 3 to the n is congruent to 1 mod 13 squared, then certainly 3 to the n is congruent to 1 mod 13. Okay, you can just sort of check the definitions of mod or modular arithmetic to make sure that makes sense, but if 3 to the n is congruent to 1 mod 13 squared, then certainly 3 to the n is congruent to 1 mod 13. Now of course 3 to the 1 is 3, and that is not congruent to 1 mod 13, and 3 squared is equal to 9, and that of course is not congruent to 1 mod 13. So that tells us that the smallest sort of power of 3, such that 3 to that power is congruent to 1 mod 13, is 3. So sort of using a similar argument to what we had before, we must have that n is a multiple of 3. Okay, so that we have that n is a multiple of 3. So let's write that down. So n is a multiple of 3, so 3 must divide n. But in particular, that means we can write n is, say, equal to 3 times m. Now, 3 to the n, that guy there, is just now 3 to the 3m, which of course is just 27 to the m. But of course 27 we can write as 13 times 2 plus 1 to the m. Now what we're going to do is use sort of the binomial theorem to expand this guy. But basically what I want to do, we want to make this guy be congruent to 1 mod 13 squared. And I claim that the smallest m for which that happens is when m equals 13. And to see that, let's just expand this by the binomial expansion. This guy equals the sum from I equals 0 to m of m choose I times 13 to the I times 2 to the I, and times 1 to the m minus I, but 1 to the power of anything is always 1. Okay, so this equals the sum from I equals 0 to m of m choose I times 13 to the I times 2 to the I. But of course, for I being bigger than or equal to 2, 13 to the I certainly is divisible by 169. So we only need to consider the cases when I equals 0 and I equals 1. So this thing here is congruent to m choose 1, which is just m, times 13 to the 1 times 2 to the 1 plus 1 times 13 to the 0 times 2 to the 0. Okay, so let's clean this up. This guy here is just 26m plus 1. Okay, or I could write that as 13 times 2m plus 1. And we want this guy here to be congruent to 1 mod 169, or mod 13 squared. So cancelling the 1's from both sides, we have 13 times 2 times m is congruent to 0 mod 13 squared. Now 2 and 13 squared are co-prime, so I can sort of divide by 2 on both sides. So I get that 13m is congruent to 0 mod 13 squared. So the smallest m which sort of satisfies this is clearly m equals 13. Okay, so if m equals 13, then n must be 3 times 13, or I should say n is a multiple of, because obviously if it works for 1, then it will work for any multiple of it. So n is a multiple of 3 times 13, which of course n is a multiple of 3 times 13, which is 39. I was about to write 49 there, is 39. Okay, so now we've got two conditions. N must be a multiple of 5, and n must be a multiple of 39. And you can check for yourself the smallest n for which both of those conditions are satisfied is when n is 39 times 5, which is 195. Okay, so that's our final solution. N is 195, because we need n to both be a multiple of 5, but also to be a multiple of 39, and the smallest positive integer which satisfies that is 39 times 5, which is 195. Anyway, I hope you have enjoyed this fun number theory problem. I'll catch you in the next one. Have a great day.